What's up everyone, welcome back to my channel. Today we're going to solve a combinatorics problem, and it's going to be finding the x sub k, where x sub k will have a form a times k squared plus b times k plus c, such that when we add up the first n terms of the sequence of x, we actually get the sum is equal to n to the third power. And in fact, we're going to see it in two different methods, where the first method, we actually need to know the facts that when we add up the first n terms of constant 1, of course, is going to be equal to n. And if we try to add up the first n terms of the natural numbers, we actually get 1/2 times n plus 1, or we can just multiply in to get the standard form, so that we will see the coefficients of n squared and n. And similarly, if we try to add the first n terms of the squares, we actually get the total sum is equal to 1/6 times n plus 1 times 2n plus 1. And again, we can try to multiply the right hand side so that we will get the standard form and know the coefficients of n cubed, n squared, and n respectively. So before we move on, you can pause the video and try yourself first to see if you actually get the same result as I do. Are you ready for it? Here we go. So for the first method, we actually will need to use the known facts that we actually have on top. And as we already know that the closed form of the term of the sequence x, meaning x sub k, it will actually have the form of quadratic. We're going to set up an equation by rewriting the results that we want, n cubed, as the left hand side of our equation, where of course the right hand side will now become the sum of the first n terms of the sequence x sub k. And now we're going to substitute what x sub k is in closed form, which is ak squared plus bk plus c. And let's try to put a parentheses here so that we know that we're doing the sum of these. And again, we know that we're adding the first n term, so I'm going to skip that part. We don't have to keep writing it. Now, since we're adding finitely many terms, the result has to be a fixed number. In other words, this has to be convergent, and we are allowed to break the closed form into parts of different parts of the sums here, meaning that since we have the absolute convergence here, we can rewrite the right hand side as the sum of ak squared plus the sum of bk plus c, the sum of c. And then we can just factor out the coefficients so that we get a times the sum of the first n square terms plus b times the sum of the first n natural numbers plus c times the sum of the first n terms of 1. So we can now use the known fact and substitute in to get that we have a times this big sum here, 1/3 n to the third power plus 1/2 n squared plus 1/6 n, plus the second term b times the sum of the natural numbers, which is 1/2 n squared plus 1/2 n, plus c times the sum of the first n terms of 1, which is just n itself here. And now we can just collect all the like terms so that we get a/3 times n to the third power, where a/3 is now the coefficients of the n cubed term on the right hand side, plus similarly we have a/2 plus b/2 quantity times n squared, where this black part is again the coefficients of n squared, plus let's see, we have a/6 plus b over 2 plus c times n, so that we can set the left hand side and the right hand side to be equal to each other by setting all the coefficients of the like terms equal to each other, and give us the following system of equation. On the left hand side, we have 1 as a coefficient of n cubed, so we have 1 equals the coefficients of n cubed on the right hand side as a over 3. And then we have 0 equals a over 2 plus b over 2. Again, this 0 is referring to the coefficients of n squared term on the left hand side, which is actually not here, meaning that we have 0 copies. Where on the right hand side, we have a over 2 plus b over 2 as coefficients. Then we have 0 equals a over 6 plus b over 2 plus c for the n term. Okay, then now as we solve the system of equation, we get a is equal to 3, b is, in fact, if we substitute to here, we'll get -3, and c, as we substitute a and b into the last equation in the system, we will get 1. And therefore, now we can just throw back all these coefficients into the closed form of the term x sub k, to give us that the sequence x has the form of 3 times k squared minus 3k plus 1. And that's it. That's how we actually get the results. And here is the first method. Now, let's jump into the second method after we erase the board. Okay, now we're going to move on to the second method, which is a lot faster. And in fact, for a second method, we do not even need to know all the known facts above, but instead we actually need to use what we call the telescoping method. But this time, instead of trying to do the telescoping method by canceling all the terms in the middle, we're going to do it backwardly, meaning that we're going to use the inverse telescoping method to actually find the results. What are we going to do? We will start with n to the third power, which is the results that we want for the finite sum. And then we're going to rewrite as n to the third power minus 0. And again, we know that anything minus 0 is just the term itself, and therefore we can always try to do plus or minus 0 however we want. And we can rewrite 0 as 0 to the third power as well. What should we do next? Since we want to try to use the reverse telescoping method, we now need to consider what we should fill in the middle. So don't forget, we still have the minus 0 to the third power at the end here. What can we do? We can just try to regroup it. Why are we allowed to do that? Again, that's because we're adding finitely many terms, and adding finitely many terms means that the sum of the sequence, or in other words, the finite sum of the sequence, has to converge. And in fact, it will be absolutely converged, meaning that we can rearrange the order however we want. And therefore, as we can rearrange the order of the sequence however we want, we can also try to combine them however we want, which would not change the result. And we can just try to group every two terms together like so. And we will actually get n to the third power minus n minus 1 to the third power, and then n minus 1 to the third power minus n minus 2 to the third power, so on and so forth, so that we eventually will get a finite sum like this. First one, we have 3 times n minus 1 squared plus 3 times n minus 1 plus 1 And then for the second term, we'll have 3 times n minus 2 squared plus 3 times n minus 2 plus 1, and so on and so forth until we have the second of the last term and the last term, where the second of the last term will just be 3 times 1 squared plus 3 times 1, and then plus 1. And to the last term, we will still write out as 3 times 0 squared plus 3 times 0 plus 1. And why do we want to write out the last term explicitly? Because now as we collect all the square terms, all the linear terms, and then all the constant terms together, we still actually end up with n terms in each column, where we will actually start from 0 to n minus 1 instead of from 1 to n. So in fact, what we get is we have 3 times the finite sum where k starts from 0 to n minus 1 of the k term, k square term, and then plus 3 times again k start from 0 to n minus 1 of the natural numbers, plus 3 times k start from 0 to n minus 1 of the constant term 1. So now we're going to do a small adjustment by shifting our dummy variable k starting from 0 to n minus 1 into 1 to n. And as we do that, we actually need to adjust the thing inside, where k will now turn into k minus 1, just like when we try to do a u sub and change our upper bound and lower bound at the same time. So we actually get this, plus for a second finite sum, we will get, instead of again k, we will actually have k minus 1 here. But then for the constant term, since there is no k that we need to substitute in, there's nothing that we need to change. And therefore, as we try to, there's no 3 here. As we try to add them together and rewrite it as just one single big term in the closed form for the sequence, we actually get 3 times k minus 1 squared plus 3 times k minus 1 plus 1. And again, we have this expression here in green. And then we just need to simplify this expression in green or inside of the brackets, so that we actually get k from 1 to n of the finite sum 3k squared minus 3k plus 1. And therefore, everything inside of the parentheses, 3k squared minus 3k plus 1, will actually be the closed form of the term x sub k of the sequence x, such that when we add the first n terms of the sequence, we will actually have n to the third power. And that's it. I'll see you guys next time.